Hello again, this is Tim Baldridge, and today I want to talk a little bit about Boolean blindness. This is a paper, actually a blog article I came across recently. And I was at the Clojure Conj recently, and I saw someone, or heard someone mention this, and their take on it, I thought I maybe didn't completely agree with, but I wanted to go read the article. So I read the article, and I actually found it pretty interesting. Um, and this kind of comes down to an area of programming where we could perhaps leverage types to enhance our knowledge about the system. But in general, it is a way of leveraging types, and I'm not sure that it is always useful, but it's useful in some situations. So what are we talking about? We're talking about what Booleans are and how they're used in programming, right? So if I came up to you and I said true, what does that do for you? If I just say true, I evaluate that in the REPL, that tells you absolutely nothing. I say false, tells me nothing. If you say to me, is the car in the garage or not? And I reply with true, that still tells you nothing. It tells you that the car is either in the garage or not in the garage, but depending on how I interpreted your question, it doesn't really tell you much. And that's what this article is about. It's the fact that when we use Booleans, true and false, we are actually throwing away information that in and of themselves, these values mean nothing. Now, I don't think it's a way of saying Booleans are bad. At some level, we have to have branches in our system, and those branches are true or false. I mean, almost everything in the system works off of, in computers, works off of 1 and zeros. But the question is, are we losing information? One way of explaining this is with the term provenance. Where did the information come from? Can we backtrack that information to figure out what has happened? And what do we mean by that? Well, if we say less than 1, 2, we get back, if I'm in the right namespace, we'll get something back. Let's try this again. There we go. I have to import the right information. So if I say 1 is less than 2, we get back true. But without this less than 1, 2, the value true is completely meaningless to us, right? So how could we fix this? Could we fix this with a set of types? And I think we actually can. And we're going to look at this as kind of there'll be a bit of an explosion of types here. But we're gonna define it like this. In fact, let's just define it as truthy and falsy. So we have truthy and falsy. Oops, here we go. Let's do it this way, falsy. And based upon this, we could actually build up a set of primitives like if and Clojure, right? So what's going to be something that's going to be true? Well, we could say 1, a number, an integer. Any integer is going to be a truthy value, right? So we could do extend protocol truthy. Actually, we might have to do this differently. I'm not exactly sure how we would do that. This might work. So our truthy types are long. Does that actually work? I don't know that we can do marker protocols this way. How about I name it right, and then that would work a little better, wouldn't it? There we go. Hey, that works. And then based upon that, we'll still have to have an if, but we could say if satisfies truthy x, then true, otherwise false, right? And x is undefined, so if we say 1, we get back true. If we have nil, we would get back false, right? This is not truthy. So based upon that, we could actually do a macro, def macro, and we would call this dash if for our if test then else, and we can actually write this, if satisfies truthy test then else. Okay, and based upon that, we can do if we can do something like if 1, true, false. Okay. What have we done so far? Well, pretty much nothing. This doesn't get us much of anything at all. But what we could start to do is to build up some Boolean-like operators off of this. So what I'm going to do is we're going to define a few more bits here. Def record. True true equal x and y. Actually, we could probably just call this equal. And def record not equal. Right? And then equal is going to be truthy, and not equal is going to be falsy. Now what is this? What does this give us? Well, not a whole lot yet, but we'll see in just a second. Now we can define a def end called, for instance, EQ for equal x and y. And we would say if equals x and y, if x and y are equal, we're going to return equal x and y. Otherwise, we're going to return not equal x and y. Okay. So now if we say equal 1 and 2, we get back an actual object that says 1 and 2 are not equal. Right? And if we have two things that are equal, well, then our result is we get an equal object back. So then if we tie this into our if, like before, we could do something with this. So 1 and 1 returns true, 1 and 2 returns false. Okay, so what does this give us yet? Well, it gives us a little bit of information. Since we now have tracking, the output of equals now tells us what the inputs were, right? It says 1 and 1 are equal, 1 and 2 are not equal. All right. So can we extend this to other sort of things? Well, yeah, actually we can. We could do something like this. Contains map val. And this would, sorry, not def protocol, def record. And this returns truthy. So we have contains and not contains. And now we can actually do something like a contains question mark, like Clojure has, map and value. And then we can actually say, you know, if contains map val, then we would return contains map val, and not contains map and val. Okay, so now we got another thing here, and we can do dash contains. Actually, we do a set here. 1, 2 is not in that set. 1 is in that set. Okay, one last thing we'll do here. For the final trick of the evening, we're going to actually implement. We can implement or and in this fashion as well. Now we could do this short circuiting, but we're not going to do that here. We're going to not do short circuiting. We're actually going to evaluate the arguments. But we can do and here, and what we can do is say. We figure out how we want to do this. So if you know, we could actually implement this as a seek, and that's what we'll do. So so if every one of these satisfies the truthy, then we're going to return true. and true of args. And we'll do so, yeah, I keep doing def protocol. And we'll start chaining this together in just a second here. So we have and true, or so that's and true is what this should be. And we could name this something else. We could say all not all. Now, what's interesting about this is, you know, we'll look at this in just a second, but it would be possible to also split the args here, right? What we're doing now, and if we do this sort of thing, we'll do dash and equals 1, 2, or 1 and 1 equals 1 and 2, 2 and 2, right? And if we run this, we get back, yes, all of these are true. 1 equals 1 and 2 equals 2, so we return all, right? Now, what's interesting about this is we could also, if one of these legs is false, we get back not all. Not all of these things are true. Now, we could improve upon this by actually dividing them up and saying which ones of these are true and which ones of these are not true, right? So instead of all, we could, and just having args here, we could have true and vowels and not true vowels. And that would actually allow us to better introspect and understand which leg of this and was thrown away, right? But we'll do this for now. And likewise, we could do or, and this one might be a little bit more interesting to do. So let's see how we're going to actually do this. Def record. We'll do sum, and then true val and args, right? And then the other record is going to be none and args. Okay. So what this or will say is the first thing we want to do, I think sum will do the trick. True val sum. I think we can just do satisfies truthy like this, and we're going to actually need to return this value. So we'll do a do. Sum should return the first thing, the result of the first function that returns true here. So if we return this, then we're going to do args and say when true, we can actually do it this way, can't we? We can say if let, and then we're going to return sum true val or false or all args, right? And we could probably even reuse some of these types, but I'm kind of coding this off the top of my head here, so bear with me. Otherwise, we're going to return none of these are true. And let's remove that. There we go. Okay, so let's see what happens when we do this. Or equals 1 and 2. So this returns a true value, that 1 is equal to 2. And if we had, oh, no it doesn't. Do we actually, okay, let's see what the definition of sum is. Returns the first logical true value. Oh, of course, because the logical true values are, yeah. So let's do, we're going to do it like this instead. And we'll just do what I was talking about before. We could actually group this by 2. This is an interesting way of destructuring, but we'll see it here in a bit. Actually, I think I did it the wrong way. T-vals. Yeah, false. You can actually destructure maps this way, where group by satisfies the protocol of truthy. So I did have it right before. Okay. You put the symbol first. I don't use this much. And then the second one is the key. Okay, so then what we would say, we're going to actually just turn this into a let and say if empty t-vals, then we're going to do none f-vals. Otherwise, we're going to do some t-vals, f-vals. And this will be a little bit cleaner of a result. Okay, so that works. So let's see. EQ1 and 1 has one thing in the true vowels, nothing in the false vowels, so some are true. Otherwise, what we're going to do is do 2, and then everything is in the none, and none is falsy, so there we go. Okay, so let's combine this a little bit. Let's say x in range 3, y in range 3. And then we're going to say EQ x and y. And we would actually need a less than, oh, here we go. And EQ equal x is equal to 2. So we're going to return a sequence of things where x and y are equal to the same thing, and x is equal to 2. So if we print this out, we get this nice big table. So let's take a look at it. So we have one result that is true, and that one result is x and y are 2, and x and y are true. That's interesting. I did not expect that to be equal. Oh, because the keys here are x and y, and that's a little confusing. We could probably change that. We probably should change that. R hand side. We're going to rename those. That's. Haha. I didn't realize that was a problem in Clojure. So okay, we'll stick with this for now. So we have one result, and that is 2 and 2 and 2 and 2, right? Because x and y are equal, and the second leg is that x is equal to, the right-hand side. But we still have all the rest of this information here, right? We still have, we know what's in one set or another. Let's do this. This might be a little more interesting. Set. Our set is the set of 2 and 0. And what we can say is we can pull in our contains and say dash contains s contains x, right? That's interesting that actually fails. I'm not sure why. But this is where we can actually debug it. So for some reason, this is saying not all of these things are true, but it's saying equal contains, these two are equal, and it's saying that the map contains 2. So I'm not sure why. Let's reevaluate this namespace. Let's try this again. There we go. Must have just something with the protocols that was wrong. So here we see, here the value is 0, here the value is 2. It's contained. We could also do this. We could say dash or. we can say where either X or Y is in the set. And here we start to see the list. So we do have one that's none, and in the case of none, we would expect, yes, that's right, the value of both of those to be 1. But everything else is pretty much true, because the only other, all these other cases, one or the other of the two values is in the map. So there's really only one case where this could fail, and that is when both X and Y are 1. And we see that as the one case. So I think this is interesting. I don't know that I'm not super sure how useful this is. I mean, obviously we could propagate this into an entire language. There's nothing stopping us from building an entire language like this. And it does has that nice artifact of truthiness is extensible, right? In Clojure, as it stands now, there's no way to really dig into an if and say, hey, this type is truthy or that type is truthy. But in this case, we actually can do that at a performance hit, right? Every single if then becomes a type check of some sort, and maybe that's not the best performance-wise. But for the simple case, in this sort of system, it works pretty well. And this is a sort of system you'll see in some rules engines and the like. If you, as another example to the problems with true and false, if you think about it, how many times, I don't know if you've ever written a logic program, or hey, a SQL program for that matter, you write a SQL query, you run it, and it just returns nothing. Right? Prolog is famous for this. You ask it a question, it returns with nope. Great. What does that tell me? That there's nothing I can do to help me debug that at all, right? Whereas with a system like this, we can actually see the decision that led us to the point we're at. Now, we do trade a lot of things for that. We trade, memory allocation, and we trade, in this case, we're trading, we have memory allocations, we have the dispatch, we have all this sort of other problems, right? If you can imagine a very big program, you may get down to the end and realize that you have this huge chain of information. The other thing we haven't really implemented here is anything that returns a value. I mean, this sort of system I think could be extended to like the maybe monad, and maybe we'll cover that in the next video. Just try to extend this to a value or not a value. Those could map to truthy and false. But I think this is the key point of that article, which I recommend reading, is that when we use Booleans like this, we do throw away information. True and false tell us nothing. In a way, it's funny to me that this really is a roundabout way of talking about what Hitchhiker's Guide to the Galaxy covered. And if you're not familiar with the book, the whole gist of it is there's a group of aliens who construct a massive supercomputer to find out the answer to life, the universe, and everything. The computer cranks for a very, very long time, hundreds of years or thousands of years or whatever it is. And if I remember that the computer is actually Earth. Earth is the supercomputer calculating this entire thing. And after all this time, they gather together to find out the answer to life, the universe, and everything. And the computer returns 42. An answer without the work showing how you got there or any sort of provenance really is meaningless. That's the video for today. Thank you so much for watching.